Take a look at this example. Integrate f of x, y, z is equal to x over the region W bounded above by z is equal to 4 minus x squared minus y squared, below by z is equal to x squared plus 3y squared in the first octant, so that's x, y, and z are all non-negative here. Okay, so the really nice thing for us, okay, so let me slow down here. How do we do this? We're going to want to come up with an iterated triple integral. To do this, we need bounds on x, y, and z in turn here. The nice thing here is that bound above by z is equal to 4 minus x squared minus y squared, bounded below by z is equal to x squared plus 3y squared. So this instantly tells us that z is between 4 minus x squared, that's bounded above by this, so that's an upper bound here on z. And our lower bound here on z is x squared plus 3y squared. So these are our bounds here on z. So now the tricky thing for us, the tricky thing for us to do is that we need to figure out what are the x and the y bounds. So in order to do that, let me draw with a better marker here. Let me draw these surfaces here. So z is equal to 4 minus x squared minus y squared. That's a downward opening paraboloid. Z is equal to x cubed plus 3y cubed. This is an upward opening paraboloid. And so like there is some curve, there's some intersection curve at which these two paraboloids intersect at. So we want to figure out for what values that, what does the curve in which these two paraboloids intersect, what does that look like? To do that, what we're going to do is that we're going to set these two, if z is equal to this, z is equal to this, we're going to set these two expressions equal to each other. So we have 4 minus x squared minus y squared is equal to x squared plus 3y squared. Okay, let's simplify this. If we move if we add x squared plus y squared to both sides, we get 4 is equal to x squared plus x squared is 2x squared, y squared plus 3y squared plus 4y squared. Divide everything here by 2. X squared plus 2y squared is equal to 2. And so if we project this region down, and we project the intersection down to the xy plane, we have the ellipse x squared plus 2y squared is equal to 2. So let me just kind of recap here. We're trying to find the intersection of these two curves here. Z is equal to 4 minus x squared minus y squared. Z is equal to x squared plus 3y squared. Find the intersection in terms of x and y. Set them equal to each other. X squared plus 2y squared is equal to 2. That's the projection of the intersection here in the xy plane. So okay, let's go to, let's draw this once again here in the xy plane. So x squared plus 2y squared is equal to 2 here. If y is 0, x squared is 2, so this goes at positive square root 2 and negative square root 2. If if x is 0, 2y squared is equal to 2, y is plus or minus 1. So this is the projection of the intersection of the two paraboloids in the xy plane. Okay, there's something else we haven't dealt with yet. We want the first octant, x, y, and z are all positive here. So x and y are both positive. So we're only considering this right here. So, okay, what are bounds on x and y here? So, I'm going to go in the order. I'm going to slice this slice this horizontally here. So y runs from 0 to 1, and x runs from 0 to this curve out here, x in terms of y. So x squared is equal to 2 minus 2y squared. X is equal to the square root of 2 minus 2y squared. We're in the first quadrant, so we pick the positive square root. Okay, so here are our x bounds. Okay, so we are now ready to write down our triple integral. So we start with y is equal to 0 to 1. So we want our constant bounds to be on the outside. X runs from 0 to the square root of 2 minus 2y squared. And z runs from x squared plus 3y squared to 4 minus x squared minus y squared. And we're integrating our function here is x dz dx dy. So let me point out here, the outside bounds are constant. The x bounds can depend on y, but can't depend on z. The z bounds are allowed to depend on both x and y here. Okay, so let's see. Let me do at least some steps of the integration here. Integrating, x with respect to z is just x times z. And so we end up with x times z, plug in z is equal to x squared plus 3y squared to 4 minus x squared minus y squared dx dy. And so this is going to be integral y from 0 to 1, x runs from 0 square root of 2 minus 2y squared of x times this minus x times this. Okay, so there is a relatively long integral for us to evaluate. It's nothing too complicated here. So in the interest of time and sanity, I'm just going to say you should end up with 16 over 15 when you crunch this out. I mean, find antiderivative with respect to x, plug in those things there, and then integrate with respect to y.